So yesterday we started talking about organic chemistry. We said organic chemistry is chemistry that involves carbon. We said that really all of the biomolecules that are important involve carbon in some way, shape, or form. So carbon makes up almost 20% of our bodies. And then we classify hydrocarbons into three main groups. Hydrocarbons, again, being carbon-containing compounds that are only carbon and hydrogen. We said the first one is alkanes. That's where we have only single carbon-carbon bonds. And then we have alkenes, where we have a carbon-carbon double bond. And then we have alkynes, where we have a carbon-carbon triple bond. And we said we can describe these in terms of saturated or unsaturated. We said saturated means you're essentially referring to an alkane. Unsaturated means you're referring to an alkene or an alkyne. And then we went through and we did some examples drawing the Vesper shapes, but we'll skip those right now. And then we talked about naming hydrocarbons. And we said that you have to be very careful with the prefix that you use. And like I said, the hardest prefixes, in my opinion, to remember are these first four. So methyl, ethyl, butyl, propyl, and butyl. After that, you're basically just describing polygons, right? So they're pretty easy to remember. The suffix depends on whether or not you're dealing with an alkane, alkene, or alkyne. And there's additional naming rules. However, I'm really focusing on this class on getting the really simple naming. There's a bunch of naming practice problems on that blue worksheet, though, if you want to take a look at them. All right. So what we're going to do today is switch gears and talk about functional groups. And like I said yesterday, I already put up a Quizlet. Functional group flashcard game and a video on here. So if you do want to review any of these at home, you can do them. It takes a little bit of practice to get used to them, though. So let's go through and just go over them one at a time. All right. So functional groups are groups of atoms with a specific connectivity. The way I like to describe these is that they are the body parts of a molecule. Right, so with a human being, you wouldn't go out and say, it's that part on the body that has fingers on it and whatnot. You'd say it's a hand, right? You want to be as descriptive as possible when you're describing a functional group, so we want to use descriptive names. So there's some really simple ones that we already covered. We said we've got alkanes, alkenes, and alkynes. Those were the easy ones. We said alkanes are always going to have CC bonds that are single bonds. Alkenes will have carbon-carbon double bonds, where alkynes will have carbon-carbon triple bonds. In my opinion, those are the easiest ones to remember, and they're kind of freebie points on exams. So take advantage of them. So let's go through and look at this molecule. And let's try to identify the different functional groups. And I'm going to highlight them different colors. So we first have to spot our alkyne. Where do you guys think that is? Triple bond, right? Alkyne with the YNE suffix is going to be this triple bond. So let's go ahead and label that. This is our alkyne. Make sure you include the right suffix, though. Okay? Next one. Let's make this one green. What is this functional group right here? Alkene with an ENE suffix. And where are the alkanes? Basically everything else, right? Everything that's not a double or triple bond you can consider an alkane. So I'll just pick one and I'll say this has got to be an alkane. The easiest thing that students mix up is they switch up alkane and alkene, so make sure that it's very clear what you're writing. Sometimes it's hard to tell with people's penmanship. All right, so those are the easy ones, but we got to start learning the hard ones now. So we'll start with functional groups containing oxygen. All right, and I really like to use these placeholders called R groups. Really, you can just kind of ignore an R group anytime you see it written. It's just basically filling in a gap somewhere. So let's take a look at our first functional group containing oxygen. These are alcohols. The general formula is really easy. The general formula for an alcohol is going to have some sort of placeholder with an OH group coming off of it, right? So let's take a look at some examples of these. Let's say we've got H3COH. What would our prefix be for our carbon backbone? Would it be F, prop, bute? What do we call it if it's just one carbon? Meth, right? And then anytime you have an alcohol, you have an OL suffix. So if we kind of merge these two together, what do you think this alcohol is going to be called? Methanol. Okay, let's do another one. Let's say we have CH3, CH2OH. What do you think this is going to be? What's our longest carbon backbone now? I would say it's actually 2, right? So these are big long carbon chain. So what would you call a 2 carbon chain? S, right? And then we said this would have your OL suffix. We combine these together, what do we get? Ethanol. Which one of these can't you drink if you're over 21? Ethanol. Methanol is actually really bad for you. If you drink it, you will go blind. There are actually stories of people purposely poisoning alcohol with methanol. So during Prohibition, there was some really shady stuff going on with the US government where they were actually spiking methanol into alcohol in order to make it unpleasant for people to drink. You know, the unfortunate side product was people would either die or go blind if they had too much of it. So ethanol is the alcohol you can drink. Methanol is the alcohol you cannot. So be sure to buy the correct alcohol. All right, let's go to the next one. Ethers. So we just did alcohols. The general formula is really similar to an alcohol, but instead of an OH group, you have an oxygen between 2 carbons typically. So there's no OH group in an ether. That's how we distinguish an ether from an alcohol. Okay, so let's take some examples here. Let's say I've got this molecule. We have to kind of break it apart into groups, so I'm going to just take a look at this portion over here. What group is that going to be? Yeah, it's going to be an F group. Specifically, it's going to be an ethyl, because we add that YL if it's a substituent. And in this case, we actually have 2 of them in the molecule. And so anytime we want to name these, we would just refer to it as diethyl ether. So the easiest way of doing this is you'd say this just means that we've got 2 ethyl groups. and there's an oxygen in between. Does anybody know what diethyl ether used to be used for? It used to be used for surgeries. They actually used to hold rags over people's faces until they got super high, and then they would do surgery on them. It's obviously not the best anesthetic out there, so nowadays when you go to the hospital, they don't pump you full of ether or chloroform anymore. However, diethyl ether is commonly used in organic chemistry lab as a solvent, so it's pretty common. All right, now let's do another set of practice. This one's on your sheet, so feel free to identify all of the functional groups that you can on this molecule. So I'll give you guys a minute to work on that. If you don't have one of the practice worksheets, grab it up front. Try to circle them and then label them. Yep.
How far do we follow the carbons to the
Just go one carbon out when you're looking for a functional group. Yeah. Yep.
So when we're labeling it, you want to just do it like alcohol or ethers, or you want to actually like...
Just label it with the functional group name. I don't want the full formal name. I was just showing you the full formal names because you might see them in other classes, and I want you to be able to interpret them a little bit at this point. If you guys go on and take organic chemistry, then I'll teach you all the naming. How many people were able to spot 5 different functional groups? A few people? Okay.
The groups only contain one carbon?
So when you're looking for a group, really only look at a couple atoms nearby, not the entire chain as a whole. So for example, this group right here, I'm looking at the carbon-carbon double bond. What functional group would that be? An alkene, right? With an ene suffix. What functional group would this one be? Alkyne. So we'll do the easy ones first. Where's an alkane? Anywhere where there's a carbon-carbon single bond, so I'll just pick one. All right, now we'll see who's really paying attention. Let's go back to the alkene. Is that a cis or a trans alkene? What do you guys think? Focus on the hydrogens. Are they on the same side or opposite sides? Opposite sides. So are they cis or trans? Trans. So we can label this alkene as a trans alkene. Okay. What other functional groups am I missing? I don't have any of my oxygen functional groups labeled. So what would this one be? Alcohol. We've got an OH group. All right, and then over here we've got an oxygen between 2 carbons, where this one was an oxygen only attached to 1 carbon. What would this be? An ether. So not too bad, right? All right, now we get to do the even trickier ones. These are called carbonyl functional groups. Carbonyl functional groups are molecules that have a carbon-oxygen double bond. Okay, so let's take a look at some examples of molecules that have carbon-oxygen double bonds. And again, I'm going to use that R placeholder. And I'm just going to say CHX, so it's got some sort of carbon attached to it. There's one where you just have a hydrogen attached. There's one where you have an OH. Let me slide this down a little bit more. And there's one where we have an OR. I have a question for you guys, though. What occurs at this blue position right there? The carbon. It's an assumed carbon, so anytime you see something like that where there's a branch or a zig or a zag, remember that that's an assumed carbon. It's kind of a time-saving technique. Okay, so let's go back and name these now. This first one is referred to as a ketone. That's where you have a carbon directly attached to a CO double bond. Oop, shoot. The next one is where you have a hydrogen attached to a CO double bond. This is referred to as an aldehyde. Next one is where you have an OH directly attached to a CO double bond. This is referred to as a carboxylic acid. This one is the trickiest one for Chem 110 students. They look at that and they say, well, it's an alcohol, right? Well, kind of. We want to be as specific as possible when we're describing functional groups. So more specifically, it's a carboxylic acid. So if you see this functional group, don't call it an alcohol, call it a carboxylic acid. It's more descriptive. All right, the next one is where you have a nitrogen directly attached. This is referred to as an amide. These are found in your proteins, right? It's your protein backbone. And then last but not least, this one is where you don't have a OH group, you've got an OR group, so it looks almost like an ether, but one side's a carbonyl. Do you guys see that? This is called an ester. So esters are commonly found in fats. So most fats have some sort of ester linkage in them. Does that make sense? So these, in my opinion, are the trickiest ones to learn. These are the ones where I would sit down with flashcards like every night before bed and just flip through them so you become familiar with them. So let's do some identification again. Here's our next molecule. Let's identify all the functional groups that we can. How many functional groups were you guys able to identify? Those of you who have finished. 6? I'd say there's 7 if you count the alkane. So if you're still working on it, see if you can spot 7. Yep.
Can you have like two different carbonyl function groups come out from one carbonyl?
So for one carbonyl, so for one CO double bond, identify the functional group for that CO double bond. So it can only have one. Yeah. So for example, I'm just going to pick one right here. Let's pick this carbonyl. What functional group do you think this carbonyl has? Let's try to be as specific as possible, right? So you could say, hey, if it's this side, it would be a ketone, right?
It's the other side.
But if it's this side, it's an aldehyde.
That's what I was wondering.
Really, for this one, the more specific one would be an aldehyde. Treat this as just basically a placeholder. You guys want to try this carbonyl? What do you think that one will be? What do you guys think? Is it going to be an ester? I wouldn't say it's going to be an ester. This oxygen isn't directly attached to the carbonyl, so it couldn't be an ester. So if we look at it, right, you could say, hey, this is a carbonyl that's between two carbons. Which one best describes that? You guys are quiet. Ketone. So ketones are always in between two carbons, where aldehydes are usually between a carbon and a hydrogen. Does that make sense? So that's an easy way of differentiating them. All right, it looks like we got our two carbonyl groups. I think we're missing a few others, though. What's this functional group called? Ether. People get ethers and esters mixed up all the time. Ethers are always between two carbons, but no carbonyl group. All right, what about this functional group? Alcohol. All right, what about this one? And let's be as specific as possible. Transalkene, okay. What about this one? Alkyne. Do we have trans alkynes or cis alkynes? No, there are no hydrogens on them, so we can't say they're on opposite sides, right? You really only have cis or trans when you're talking about alkenes. And then last but not least, we could just pick one of these and we could say, hey, this is an alkane. So you will most definitely see problems like these on the exam. The big thing is to make sure that you remember each of the functional groups and that you don't flip ethers and esters and things like that. Oftentimes people flip the names for some of the ones that sound similar. Let's do the last one. Give you guys a minute to work on this and then check with your neighbor. And if you think you got them all, give me a thumbs up too.
instead of placeholder?
So the R group is usually a hydrocarbon, so treat it as a carbon placeholder.
But I mean, like on the left-hand side, there's an N, but there's no placeholder attached to anything.
So in this case, it's got two hydrogens, so in that one example, the hydrogens are attached to the nitrogen. Amides are kind of weird that way. There's a bunch of different types of amides. The way I always spot an amide is you've got a nitrogen directly attached to the carbonyl. Doesn't matter what else is attached to that nitrogen. I guess I gave away the first one. This functional group, what was that called? Amide. Oh. All right, what about this functional group? So there's no CO double bond. It's an oxygen between two carbons. Neither carbon's a carbonyl. Which one? An ether. All right. We'll do an easy one as an ego boost. What's this one? Alkane. All right. And then over here, we've got a different one. I'm going to change colors. What would we call this one? So we've got a carbonyl. We've got an oxygen attached to it, but it's not an OH. Which one? Ester. All right, and then over here, what would we call this one? Alcohol. And then down here, alk, Y and E. So make sure you use the Y for the triple bonds. Then this one right here, let's be specific. Transalkene. And then what about this one? Carboxylic acid. These are different than esters because they have an OH directly on them. Just random question, not to judge anybody. How many people have heard of these functional groups before in other classes? It's a little bit in like general chemistry in high school or biology. Where did you guys learn about these? Biology? Okay, so for some of you, these might be a little bit of review. For others, it may sound like a foreign language. However, I would try to study either way. They're really easy to mix up, and they require a little bit of practice to get good at. Here's one last functional group, but this one's a bit easier than the others. This has to do with rings. So in organic molecules, you oftentimes see what are called aromatic rings. What does aromatic normally mean? Like if you think about it in a grocery store, if something's advertised as aromatic, it smells good, right? So aromatic molecules were normally thought to smell good. There's a whole bunch of different aromatic molecules, but we're going to focus on benzene rings. These look like a Ferris wheel almost, where you've got 6 carbons attached. And then you alternate double and single bonds all the way around the ring. So I'll go double, single, double. And then each of these carbons has a hydrogen on it. This is referred to as benzene. What do you think this would look like with bond line structure, where we don't show all the carbons and hydrogens? Like a hexagon, maybe? So we'd have double, 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 and then singles in between them. So oftentimes you'll see it written in the way on the right-hand side, simply because it's a heck of a lot easier to draw it that way. These are really common. This is found in gasoline. However, it is a carcinogen, which is why it's a bad idea to huff gasoline, and it's only present in trace amounts. So benzene is really interesting. There's a whole bunch of chemistry that you can do with it to make it into perfumes and food additives and things like that. Does that make sense? Okay, what we'll do is a few practice problems. And then we'll, if we have time, go into some more advanced naming. Which of the following organic compounds is most likely a liquid at room temperature and why? If you think you got it, try to explain it to your neighbor. So let's go through really quick and identify how many carbons are in each of these. So methane, how many carbons? 1. Ethane. 2. Propane. 3. Butane. 4. And then 5. So the real question is, which one's more likely to be a liquid? The heavier one or the lighter one? Why do you think the heavier one?
Because the melting point is higher. Everything else starts to boil.
Okay, what intermolecular force would cause it to have a higher melting point and higher boiling point? Dispersion, right? So larger molecules have more dispersion forces. Which means that they have higher boiling points and melting points. Methane, we said, is a gas. It's found in natural gas, so we know that that isn't going to be a liquid at room temperature, right? However, pentane, because it's a lot bigger, is attracted to other pentane molecules and has a much higher boiling point. Does that make sense? Okay, let's go to the next one. Following chemical belongs to what family of organic compounds? And they built a model for you. Alkenes, why an alkene? Carbon-carbon double bond, right? What's an alkane again? 1 bond. Alkynes? 3 bonds. Aromatics? It's a Ferris wheel of alternating double single bonds, right? And aldehydes, what are aldehydes? This is where we had that R group, carbonyl, and then a hydrogen directly attached, so it most definitely doesn't look like that, right? So in this situation, alkenes would be the best answer. Right, let's do another one. Which functional group does the following chemical contain? And red balls are oxygen, black balls are carbon, white is hydrogen. Kind of. Well, let's identify this one on the left. So if the white balls are hydrogen, right, and I look at it and I say, all right, what's this functional group? Is it going to be a ketone? Nope. Aldehyde. So maybe it's that. What about this one? Looks about the same. It's an aldehyde. What about this one where you've got carbons on both sides? It's going to be a ketone. So we're kind of stuck right now, right? It says, which functional group does the following chemical contain, meaning all of them? So can't be an aldehyde or ketone. Can't be an alcohol because we don't have an OH. What's a carbonyl again? All of those. Carbonyls are any molecule that contain a CO double bond. There's a bunch of them. We said we've got carboxylic acids, esters, aldehydes, ketones, amides. They all are similar in that they all have that CO double bond. So carbonyl just means CO double bond. All right. Which of the following compounds would you expect to be responsible for the fragrance of pears? This one's a little bit tricky. I'll give you guys a hint. esters are the smelliest molecules. So let's try to use process of elimination. What's the top one, A? What sort of molecule do you think it will be if it has an OL suffix? Alcohol. So this one's not going to be it. That's not an ester. What do you think this next one's going to be? Ketone. That one's pretty easy. It's in the name. Ketones don't generally smell that great. What do you think the next one's going to be based on its name? An aldehyde. Some aldehydes smell good. Most of them smell pretty bad. In fact, some aldehydes smell like rotting flesh or fish. They're really stinky. There's the next one that's an ether, right? That's in the name. So it's not going to be that one. The next one is actually going to be an ester. So this 8 suffix is for esters. I'm not going to be picky about the full formal naming of these, but by process of elimination, we know that this one's going to be the best one, given the hint that I gave you. If you're interested about these fragrances, I think there's a little section in the book that talks about them more. It's pretty interesting. I don't know if many of you are old enough to drink beer or drink beer, but oftentimes the smells that you get out of beer and wine are actually esters, and they have yeasts that are specifically designed to make certain esters over others. So some beers smell like bananas or grapefruits or things like that. It's pretty interesting. All right, I think we have one more. Many natural and synthetic fibers such as silk, wool, and nylon all have this functional group in common. Amide, right? What is D? That is correct. In fact, those of you that have served in the military or in the police have probably worn Kevlar vests, right? Kevlar vests have these amide functional groups in them, right? Amides are incredibly strong. One of the coolest applications I've heard of recently is the new satellites that we send up and the space station parts are coated in Kevlar. Does anybody know why? Space debris, right? You could have a grain of sand fly through your spaceship, but if you've got a Kevlar net to catch it, that will prevent it from puncturing holes in your spacecraft. So these are incredibly strong bonds, which is good for us because they make up the backbone of all of our proteins, right? We don't want our proteins to randomly fall apart on us. We want them to stick together. All right, we've got a little bit of extra time, so I'm going to do one more thing. This is kind of our bonus round. Advanced naming for hydrocarbons. It's really not that bad to name these, so I did want to introduce you guys to them. The first thing you do is identify your longest continuous carbon chain. And this will be your parent chain. 2 is identify branching groups. And then 3 is number your longest chain. So that your first branch is at the lowest number. So I'll show you guys how to do this. It's pretty straightforward though. So I'm going to make up a molecule, and I'm going to do this in bond line notation just to keep things simple. Let's do this one. What's our longest carbon chain that's continuous? So what I would do is look at this and I'd say, well, we could go 1, 2, 3, 4, 5, 6. That would be our longest continuous chain. So what would we call that in terms of our prefix? Which one? Hepta is 7. Hex, right? So this would be a hexane, right? So 1 through 6 would be hexane. All right, and then over here what we have is basically a group coming off carbon 2. The group coming off of carbon 2 is only 1 carbon long, so what would we call this? Be a meth substituent, right? Specifically, if it's coming off your parent chain, you want to add your YL. This indicates that it's coming off. So when we go ahead and we name this, what we've got to do is we would call this 2-methyl to indicate the methyl groups coming off of carbon 2. And then we'd say 2-methyl hexane. What's that?
Is it 2?
So that's indicating that the methyl group is coming off carbon 2, not carbon 3, not carbon 4. It's coming off carbon 2 on your longest chain, right? So that's a really simple way of doing this. The common mistake I see people make is they'll say, well, why don't I go 1, 2, 3, 4, 5, 6? And in this case, why don't we call it 5-methyl hexane? Which rule did we say we want to use? Number 3, we said number your longest chain so that your first branch is at the lowest number. That blue numbering pathway has a methyl group at carbon 2, which is preferred over carbon 5. So it's a lot easier and simpler if you focus on having that first branch at the lowest number. So the green one wouldn't be the best way of naming this. The blue one would be. Does that make sense? Do you have a question?
Yeah, I don't really know how to ask it. That was what I wanted to ask.
It's okay.
How do you always put like the methyl group or like what's coming off first in the name?
Yeah, you always put your branching point first and then your parent last. So the longest chain always goes last, right? Chain goes last. Branching goes first. All right, you guys want to try another one? Let's do one more. Let's do this one. First thing we want to do is identify our longest continuous carbon chain. What's the longest chain of carbon atoms that you can find? Yeah, going straight across, so 9. Oftentimes students will get tricked and they'll say, well, why not 1, 2, 3, 4, 5, 6, 7, 8? That's an 8 carbon chain. But then I would argue, hey, there's one that goes 1, 2, 3, 4, 5, 6, 7, 8, 9. The blue pathway is longer, so that's going to be our preferred numbering. Okay, so we've got our parent. So in this case, our parent is going to be what? A nonane. Because we know it's an alkane. Okay, and then what would we call this substituent if it's 2 carbons long? It's not going to be methyl. It's going to be an ethyl. So we do F and then the YL to indicate that it's a substituent coming off of something else. All right, so now we've got to kind of hodgepodge this into one big name. So the substituents go first. we need to indicate where the substituent's coming off of. So what do you guys think we should call this? 4-ethyl nonane. So 4-ethyl indicates that that ethyl group is coming off of carbon 4, and nonane indicates that our longest continuous carbon chain is 9 carbons long. So this is kind of how chemists speak to one another. If you want, you can draw the molecule, but oftentimes it's easier just to write down the name, right? So we're going to leave it as simple as that. I'm not going to go into the super advanced naming for aldehydes, ketones, esters, or anything like that. If you guys have any questions, feel free to go to the SI session, email me, stop by my office, anything like that. We want to make sure that we're nice and comfortable with this before we go into polymers and biochemistry.